Hi, this is John Whitaker for the Mathematical Analysis class, and this is our 10th video lecture. And last time we talked about certain classifications of sets, whether they be infinite, finite, countable, uncountable. And I want to start off today talking about a sequence, and then we'll get back to those types of classifications of sets and facts about them. But start off with a definition, and it says a sequence. And so what we mean by a sequence is an infinite sequence. Is a function defined on the set of natural numbers J. If we call the sequence F the function, and we say it acts on n, relevance of natural numbers, and we write down the output values as x of n, we traditionally denote the range f of j as equal to the set of all x of n's, n runs from 1 to infinity here, which is equal to x of 1, comma, x of 2, comma, x of 3, comma, forever. And x of n is called the nth term of the sequence, a little bit more information associated with this definition is if A is a set and x of n is an element of A for all n element of J, then we say, or then x of n is said to be a sequence NA. Here's a fact that I'd like to prove, is that every countable set is a sequence of distinct terms. So we can relate countable sets to sequences. Okay. Okay. So this is not something that we're going to prove, but this allows us, this fact, to order, if you will, the terms or the elements of a countable set. Okay. Here is a theorem that we will prove. says every infinite set of a countable set A is countable. So the proof is we let A be countable, and let's let E be a subset of A with E being infinite. So what we do is, using that previous fact, we arrange the elements X of A in a sequence X of N of distinct elements. So now we construct a sequence n sub k, or x sub n sub k, as follows. Let n sub 1 be the smallest element of the natural numbers, such that x sub n sub 1 is an element of E. Let n sub 2 be the smallest natural number bigger than n sub 1, such that x sub n sub 2 is an element of E. And we continue this process. To form the sequence x sub n sub k. Now, putting, as the symbols here indicate, f of k equal to x sub n sub k, then f is what we formed here, a one-to-one correspondence between E and J. Okay? Okay, so J's elements look like K, and E's elements look like exponents of K. So E is equivalent to J, and thus E is countable. So that's that proof. We next want to look at a definition. It says, let A and omega be sets, and suppose with each element alpha in Big A, there is an associated subset, we call it associated subset of omega, denoted by E sub alpha. Okay, so that's a subset of omega. Then A is called an indexing set and the set of the collections of sets, E sub alpha, such that alpha is an element of A. Okay, so that's a set. It's a collection of sets or sometimes we call it a family of sets. Okay, so we have that definition. Okay. In terms of notation, the first thing I'm going to talk about is you can have a set S equal to the union for all alphas in A of E sub alpha, and what that's equal to the set of all x's in omega such that such that there exists an alpha element of A with X is an element of E sub alpha. So what does it mean to be in this union? Well, this union is the collection of all objects from omega such that X is in one of the E sub alphas, at least one of them. And the second thing in terms of notation, we could have S equal to the intersection. Oh, wait a minute, there's more of that I want to say for this first situation. It says if A is equal to some J sub n, then in this situation where S is equal to the union, or this S is going to be the union, is I runs from 1 to n of E sub I, if you will, which equals to E sub 1 union, E sub 2 union, and you keep unioning up to get to the set E sub n. Okay, the second notation has to do with intersection. Second. And then we could have S equal to the intersection of alpha element of A of E sub alpha, which will be equal to the set of all x's in omega, such that x is an element of E alpha, and that's true for all alpha element of A. If A is equal to some j sub n, then what we have is that S is equal to the intersection, maybe a diagonal from 1 to n, of E sub i's, which equals to E1 intersect E2, and we'll keep doing these intersections till we get to the intersection of En. And we talked about set theory in lectures 2, and so we know about intersections and unions. But let's look at some examples. If we let EI be equal to minus, the interval, minus 1 over I to 1 over I, okay? Where n is an element of the natural numbers, or I is an element of the natural numbers, j. Then the union, as I run from 1 to infinity, if you will, of EI. So here, this is going to be equal to minus, well, it's going to be equal to the union as I run from 1 to infinity of, here this is going to be minus 1 over I up to 1 over I as intervals. And so we're adding all these things together, if you will, grouping all these intervals together. But it turns out that when I is equal to 1, you have from minus 1 to 1, and that contains all the other forms of the EIs. And so this answer is from minus 1 to 1. And now let's look at an intersection of these EIs. So, also, the intersection as I runs from 1 to infinity of EI, which equals to the intersection as I run from 1 to infinity of minus 1 over I times 1 over I, is equal to, well, it's the only thing that's in all of these sets is 0. So it's the set containing 0. Okay. And some facts having to do with set theory. If A, B, and C are sets, then one of the things we have is A union B is the same thing as B union A. So the order in which we intersect them, union them doesn't matter. But also the intersection holds true too, in terms of order not mattering. A intersect B is the same thing as B intersect A. That's the first fact. I'm not going to prove that, I'm just saying that that's true. There is one of the statements that I'll make that I will prove. The second statement, having two parts, is that A union B, then union with C, is the same thing as
A union B union C. Okay. And similarly, if you have A intersect B, you do that first, and then you intersect that with C, that's equal to A intersect the quantity B intersect C. And then thirdly, if you have A intersect B union C, that's the same thing as A intersect B union A intersect C. And for this last fact, I'm going to show, first of all, I'm going to prove it, but we'll do a pictorially representation using something known as Venn diagrams. So here, what I'm going to do is I'm going to first draw the generic Venn diagram with three sets. There's A, there's B, and there's C. And when I take B union C, that's everything here, B, everything that's in B, plus everything that's in C, so I get this other part here. So I'm highlighting what B union C is. And so now, A intersects B union C. That picture, so I look at this picture, okay, and I see what does it have in common, that's what intersection means, with A, and so what I get to highlight is this part. Okay, now that's the picture, the pictorial representation of A intersect B union C right there. And when I do the pictorial representation of A intersect B union with A intersect C, I'll get the same picture. So they must be the same. But that's really not a proof in terms of symbolic representation, which we'll also do. So note A intersect B, when I draw it, it's this part right here. A intersect C, there's A, there's B, there's C. So A intersect C is this part right here. Okay? And so A intersect B union with A intersect C. So I have these two objects and I combine them, if you will, plus them. And so here it's A, B, and C. So I take all of this region and I add to it all of this region. And so this set is represented by this picture. And if you look, that picture is the same as the picture over here for A intersect the quantity B union C. So A intersect the quantity B union C must be equal to A intersect B union A intersect C. But we're going to do a proof of that in just a second. Let me go back here. Give you a chance to write this down if you need to. We're going to prove this statement with symbolically. And it'll take a few minutes. Okay? So, symbolically, so here's the statement again. In fact, it's the same one, okay? I'm not putting up anything new. A intersect B union C is equal to A intersect B union A intersect C. That's our fact. And here's the way that we show two sets are the same. So from when we talked about set theory, two sets are going to be the same, this set and this set, provided that everything in this set is in the right-hand set, everything in the right-hand set is in the left-hand set. They're subsets of each other. That's what we got to prove. Okay, so proof. So we start off by letting X be an element of A intersect B union C. What does this mean? Then, to be in an intersection means you have to be in both of these sets. So X is an element of A, and X is an element of B union C. Okay? So that means that X is an element of A, and X is an element of B, or, to be in this union, X is an element of C. So one of those two has to happen. Okay. So X is an element of A, we know that, and we have two cases. Further possibilities. To consider, and that is case 1 is X and B, and case 2 will be X and C. Okay, so case 1 is X is an element of B. And so, since X is in A, we have that X is in both of them, so X is in the intersection of A intersect B. If X is in that set, it's in that set union anything. And in particular, I'm going to union it with A intersects C. So that's a true fact. And so we have shown that if you give me something in the left-hand set, it's got to be in the right-hand set in this case. Case 2 is if X is an element of C, then we have that X is an element of A intersects C. So it's in the that set union anything. So X is an element of A intersects B, union A intersects C. Because X is in this set, so it's in this set plus some other set. Thus, in all cases, thus we have shown that if you give me something in the quantity A intersect the quantity B union C, the left-hand set, then it's in that same set is in X, that same set is in A intersect B union A intersect C. So we've shown that A intersect the quantity B union C is a subset of A intersect B union A intersect C. To show equality between these two sets, I now have to show that this right-hand set is a subset of the left-hand set. Okay. So now we let X be an element of A intersect B, union A intersect C. Okay. Then X is an element of A intersect B, or X is an element of A intersect C. So at least one of those has to happen. So we have two cases. Okay, so case 1 is that X is an element of A intersect B. So that means X is an element of A and X is an element of B. So, since X is an element of B, X is an element of B union C, because it's in B. So, X is an element of A intersect B union C, because it's in A and it's in B union C. Now for case 2, what we have is, if we let X be an element of A intersect C, second case we could have, then similarly, it's the same thing. X is in A and X is in C. Since X is in C, then X is in B union C, because X is in C. So what we have is X is in A and X is in B union C. So that says X is an element of A intersect B union C. So, in all possible cases, that said that A intersect B union A intersect C was a subset. It's a subset of A intersect B union C. And that's the proof. Well, I'll make one conclusionary statement. Thus, A intersect B union C has got to be equal to A intersect B union A intersect C. So that's what we want to prove. We did by showing that they're subsets of each other. Now, these types of unions and intersections, countably many, they're going to come into play for us later on in this class. As a matter of fact, we're going to look at a fact involving these types of unions, and here's a theorem. We're going to look at it next. So it says, let E sub n, okay, where n runs from 1 to infinity, be a sequence of countable sets. Okay. And S equal to their union. Then S is countable. It's a famous fact in mathematics, and it says the countable, what do we say? It's the countable union of countable sets is countable. That's the way that we say it. And so when we say E sub n is a sequence of countable sets, we're saying that each E sub n is countable, meaning the number of elements that it has is the same as the natural numbers. Okay. remember we had this fact, we're ready to prove it. We had this fact that every countable set is a sequence of distinct terms. We had that fact. I didn't prove it, but we had that fact. We're going to use that. And so when we start to prove, let's remind ourselves, let E sub n be countable, be a countable set. For each n's natural number, j. And so, for each n element j, the elements of E sub j, of E sub n, I should say, can be arranged in a sequence. We'll call them x sub n sub k, where k runs from 1 to infinity. Okay. So we consider the infinite array. Okay. So look, the first E sub 1, it has terms x sub 1, 1. Then next term, x sub 1, 2. X sub 1, 3, and forever. Then the next set, E sub 2, has this first term is x2 sub 1, let's write it down here with a little separation, x2 sub 2, x2 sub 3, and it goes on forever. And then we have x 3 sub 1, x3 sub 2, x3 sub 3, and this goes on forever down. Okay? And so the way that we count them, okay? So let me say a little more details. And I'll rewrite this up here. Grab a little bit more space. Okay, so here's what I have. Here's what I just have written. So we have this x11, x12, x13, x14, it goes on forever. And that's E sub 1's term of elements. And then we have x21, x22, x23, x24, and it goes on forever. x31, x33, x32, 33, x34, and that goes on forever. And it goes on forever in this direction, just keeps going forever like this. Okay? All right, and what we say is in which, I just repeated what I had written down the bottom left board. The elements of E sub n form the nth row. Okay? And then, here's what we do. Here's the way we count them. We count them diagonally. So this will be our first guy. This is our second, our third guy. Here's our fourth, fifth, and sixth guy. So we count them in this diagonal pattern. Arrows going from left to right. Okay? Okay. So as indicated by these arrows, okay, the elements can be arranged in the sequence okay, so our sequence is, it's going to be x11, comma, x21, the next one is x12, the next term is x31, the next term is going to be x22, and so forth. So we can make a sequence out of it.
But they might not be distinct terms. Okay, so let me make a note of that. So here's the note. If any two of the sets of the way we denote them, ENs, okay, have elements in common, they will appear more, they will appear, or these elements, will appear more than once in our ordering of the elements. Okay. So what we want to do is we want to remove them. These repeating elements in our sequence. Okay, so look, some of these might be repeating, and what we're saying, just take them out and look what you have left. Okay, I'm going to leave this here. And what you have there is what S is, okay? So S is the set of elements from our sequence after the repetitions have been removed. Okay? And then what I wanted to say to you is that we should note that that there are infinitely numbered of elements in S as E sub 1 is a subset of S and E sub 1 is infinite. Okay? So S then is equivalent to an infinite subset of J, let's call it something, say T. Thus, we have S is equivalent to T, and T, since it's an infinite subset of J, is equivalent to J, so S is equivalent to J, so S is countable. And that's what we want to improve. I want to go back and look at the way that we diagonalize the terms of S in this array. So I'm going to go back to that. And, we did them x of 1, x of 2, x of 2, 1, x of 1, 2, and in this way. And so what I wanted to give you was a little bit more details about that. So the one-to-one correspondence between the array and the set of natural numbers, J, here before we took out any of the repeating elements, can be seen by partitioning J using, so here's what we have. We have D minus 1 times D all over 2 is less than N is less than or equal to D times D plus 1 over 2. Okay? And their D number of N's for any particular D here. Okay, so look, when D is 1, okay, so this is going to be 0, so N's got to be bigger than 0. And then here when D is 1, we get 2 over 2, that's 1. So N is equal to 1, okay? And that is this guy here, okay? When N is equal to 1. When D is equal to 2, what we have is when D is equal to, this is 1 times 2, that's 1, so N's got to be greater than 1. And this is 2 times 3 over 2, that's 3. So in that segment of the natural numbers, we got N equal to 2 and 3. That's 2 and 3 here, okay? That's what then for D equal to 3, and I'll stop belaboring the point. This is 3, N's got to be bigger than 3, and this is 6. So 3, 4, 5, and 6. This is 3, 4, this was 4, was bigger than, N had to be bigger than 3. This is 4, 5, and 6. And that's the way we start labeling. So that gives you some idea of the correspondence. And I'll write up a little bit more details, just a second one. Not that it's that bad, just a second one. So we think of D as the deep diagonal which contains D entries. Okay, that's all I want to say. Okay, I think we should write up this last corollary, improve it, and then call it quits for this lecture. So we suppose A is at most countable, and for each alpha element of A, B alpha is at most countable. Then put T equal to the union of the B alphas as alpha's element of A. Then T is its most countable. T is at most countable. So T is at most countable. the proof. One type of situation is just like the proof that we had before.
So what we do is we let every element of B alpha be arranged in a row and consider the array so x alpha sub 1, x alpha sub 2, alpha sub 1, 2, forever, and then x alpha sub 2, 1, x alpha sub 2, 2, and I said forever, but it may not go on forever. And so forth. Okay. So here's the thing we say. If A is infinite, and each B sub alpha is infinite, okay, then this array is similar to the array in the previous proof. Okay. And in this case, T from this set will be equivalent to S and thus countable. S is from the previous proof. If not, then T can be thought of as equivalent to, let's say, K, a set K. Let's call it instead of set K, let's call it set D, which is a subset of script S. And thus is at most countable. Because could be equivalent to S, but it might be smaller than that, so it can count. Be finite. So therefore it's at most countable. Okay, that's enough for today. Thank you very much.